So we'll wait for a couple of yeah, we'll wait for a couple more minutes so that everyone can join, and then
Wonderful.
I think we can get started.
okay, yeah,
Sure.
just a second. So is my screen visible?
Yeah.
Okay,
Yeah,
great.
so should I start?
Yeah.
Yeah,
Yeah.
I think we can
Okay.
start. And hello everyone. Um, we are AiQyaM, and I would just give it to Archit so that he can start with the presentation.
Yeah. So thank you, Abir, and hello everyone. Good morning, good evening, good afternoon. And first of all, thanks a lot for being here at this event. And yeah, so today is our launch event for the community that we are trying to build around quantum hardware. And so talking about AKM, so it is a community which focuses specifically on the growth and collaboration of people around quantum hardware, so that mm, the research and development in this field can grow more effectively in future. So AKM meaning unity or oneness, and that is our centric idea that we have followed, and we are trying to build this one community which can have uh, different types of people who have different backgrounds, and then they collaboratively work together and develop uh, a single community towards it. So moving forward with the presentation. So these will be a few topics that we'll be touching in the presentation, and we'll have a talk from our keynote speaker, Zlatko Miner. So first I'll take you through who the initial members in the team are. Then I'll talk about who we are, and then Nilay will take us through the motivation, and then Abir will take us through the vision, mission, and the roadmap that we have in future. So Abir, if we can move forward. So talking about the team. So currently, the team is comprising of us, the three founding members of this community. So we have Abir, we have Archit, who is me, and we have Nilay. So giving a brief introduction about us three, what we have done in the past. So Abir is currently a student doing MS in Electrical and Computer Engineering in Duke University. He is a Qiskit advocate and is presently working on OpenChasm under Jack Moore. He is one of the founders of Quantum Hardware Learning Circle at QCI and Circuit Quantum Research, a student-focused community developed at RV College of Engineering. Abir has been a previous intern, a quantum computing intern at Robert Bosch, and he has worked on the development of benchmark application benchmarks. And Abir is motivated to work in trapped ion quantum hardware and superconducting qubits. Then if we move forward, so this is a brief introduction about me. So myself, Archit, and I have recently completed my studies, my bachelor's degree in electronics and instrumentation engineering from RV College of Engineering, Bangalore. I too was a founder of Circuit Quantum Research at RVC, and one of the founders of the Quantum Hardware Learning Circle in QCI. I previously was a quantum computing intern at Boson QCI Private Limited, and currently I'm working with Hewlett Packard Enterprise in Bangalore as a data analyst. And like my interests are to look out for ways and methods to integrate quantum computing in the field of gravitational wave astronomy. Now, moving forward, Abir. So we have Nilay with us, and Nilay has graduated with a BTech degree from Amity University, and he has majored in electronics and computer engineering with minor in embedded systems engineering. Nilay too was one of the founders of the Quantum Hardware Learning Circle at Quantum Computing India, and he's presently a research assistant at Center for Nano and Soft Matter Sciences in Bangalore. And Nilay is also a certified quantum consultant from IBM Quantum. So moving forward with the presentation. So I'll just give a brief about what our journey has been up till now. So the journey, this like special journey for us started a year back when me and Nilay started as an apprentice in Quantum Computing India in September 2020. And we worked together in the fields of quantum cryptography and quantum hardware, and we developed co-creation in Quantum Computing India, and brainstormed on different ideas. And this sparked the sense of community building and how community building can help us achieve more than what we can think of. And we worked around a lot of use cases, even use cases which feels crazy right now to us, that we even thought about it. And it was the building process of at that time which has helped us to reach at this moment right now. So in the same process, we delivered a few talks in the peer learning sessions that used to happen at weekends in Quantum Computing India. And then Abir eventually joined us, and we all three then settled on to one topic, that was quantum hardware, and we found our passion in that. And we started a Quantum Hardware Learning Circle in QCI in May 2021. And in that week, we have conducted a few sessions with Qiskit Metal and Qiskit Pulse, and we had like-minded people with us who were working with the same passion that we have. And we currently have 10 members with us who have the same passion and the same kind of enthusiasm that we all three have come up with. And this whole journey, I have summarized it up. A lot of things I did not include, but this has actually helped us shape what we are, who we are today, and what we aspire to be in the upcoming future. And the ideas that we have implemented and that we have right now that we want to implement is the result of the process that we have been a part of. So just being optimistic about what future is having for us, and how it will shape us in the upcoming few days or few months or years. So with that, I'll give it to Nilay, who will take us through what has motivated us and how we are moving forward. Oh, before that, I'm really sorry. So I'll just take you through a few of the achievements that we have achieved till now. So recently we got selected for the Rome Researchers Scholar Program, and that has granted us with access to its platform. So Rome Research will I think Sam will tell us about more at the end of the PPT. And so Rome Research has been is a platform which can be used for collaborative work, and it is a really efficient tool that can be a note-taking tool that can be used to curate content and develop it accordingly. And then recently we got accepted for the AiQyaM Quantum Educator program, and we are planning to develop quality educational content on quantum hardware and around it. So I think I'll now give it over to Nile.
Thanks, Archit. Am I being audible?
Yeah.
So moving forward with that motivation, which the main driving force which we actually got through. So it was like, especially if you see in India, like we still, like, though many communities at the college level and at the national level, we're working with like different faculty development programs, and many things are going now in developing the quantum ecosystem, but still, like, it's always good to have an extra effort coming in. So that was like one of the major motivations which we got. And if we see specifically quantum hardware, we three were generally not the fanboys of quantum machine learning, but from an engineering, we had much more into the hardware side. So if not seeing in India, but if you see at a world at a larger scale, so hardware is something which is much more kept inside the labs. People just do it inside the labs, and it's not so if you see how do you make it, and you don't have a actually clear blueprint out in the market, like how do you have for different documentations regarding the software packages available. Like you have tons of quantum software packages on GitHub out there, but you wouldn't find a lot much more clearer information which is there on the quantum hardware side. So something which we all did, like especially we three of us, when we were trying to learn about the quantum hardware, like just the basic about the different qubits. So it was like we need to look through various different research papers, but that time the jargon got too complicated for us. So it took a lot of time for us to get that, put that sequence thing. So we thought like just ease out this journey, and since it's not been done, so like be the first one to try it and just do it. Like basically open source quantum hardware learning methods, like how it's there for the software's one. And then eventually you develop a streamlined flow where a person, like from the beginner level, he can understand, or like she can understand the things, and then move forward into the quantum hardware thing. So there was a need to unify these scattered communities under the one roof, because people are totally progressing. So once, like a name, AiQyaM basically means unity in Sanskrit, so which basically means everything comes together. And in quantum also, like after the superposition, we just have one state as an output. So that is something which was okay. I'm sorry for that. Yeah, someone. Okay. So with that thing, so, and the second one was that, like, yeah, so you only grow with much more collaborations. So it's not like you can't be like one single entity just working it on. So we need to have, like, with the community, we need to get much more into the research part, and then slowly work on your own co-creation projects, and then you eventually move forward. The next slide. So yeah, so as we said, so like there isn't any quantum hardware centric community, all focus on the software side and the other aspects of quantum. So that was something, because it's like you need to have the bridge to link from one island to the other, so that, I mean, the two islands are like for the hardware, so you need to have some group of people who actually work it out, and then okay, hey, there's a plan, we, if you go this way, we have done it and it helped us, so if you go this particular way, it will eventually help you guys. So, and then it was like, again, the same story revolves again, that it was like an empty island and we didn't really have a lot more into it. And as there was a huge gap, like between the understanding the research paper and then the knowledge which was there openly everywhere, so that was a huge gap there between. So we were trying to come up with this idea and try to fill up that particular thing, so we can have like one extensive documentation where you learn about quantum hardware, and we try to get it with the minimum efforts. And pivot, or you want to take the hardest way, like go from like starting to the end, so you get the entire picture in just one frame. So like in the market everywhere, and it's known, like there is a paucity of open source software for hardware design, and right now there are just a couple of them. One is Qiskit Metal and the other is KQ Circuits from AiQyaM. So with that, I would like to introduce the speaker to for today's session, Zlatko Miner. So here's Zlatko.
Hi, Nilay. It's great to be here.
Yeah, so just giving a deja vu. So where are you tuning in from?
Now I see somebody's been watching my seminars and using my tactics on me.
Yeah,
I'm tuning in from California today. Well, I should say this evening. It's almost 10 p.m. in the evening here, but I couldn't miss this. So this is great. Thank you for inviting me as your keynote speaker.
yeah. Just a little bit introduction. Everyone knows about Zlatko Miner. So he's a research staff member at AiQyaM Quantum. And he has done his PhD from Yale University, his bachelor's from UC Berkeley, and he is the PI for the Qiskit Metal. And I guess everyone knows, I'm just repeating everything which is in the minds of everyone. So let's just move forward, and I give it to you, Zlatko, to take it on.
Thank you very much, Nilay. Well, first of all, thank you again for the invitation. It's a pleasure. I'm actually really excited and thrilled by what you guys have already accomplished here. I mean, you say that this is the launch meeting, but I mean, already so much has gone into this. So kudos to you guys for organizing this, and to everybody else who's tuning in now, because I think, like you identified, there has been a gap. And I mean, it's 2021. And like you said, I mean, Qiskit Metal didn't exist until like 6 months ago. That was the public launch date. That just happened, right? And the whole ecosystem rests on quantum hardware. So I have a few slides to share with you about, I think, the bigger picture of things. And I think you guys have already curated a lot of content and have a lot of ways to lead folks and bring them up, and we can and kind of educate folks deeper about the physics of it. So we'll do like a 20-minute quick talk. And after that, we can jump into a short Q&A. So I'll kick it off here. So tell me you can see my slides.
Yeah, we can. Yeah.
It's visible.
All right, perfect. And if you have a very burning question during the talk, that's totally fine. You can interrupt me. Otherwise, we'll save them for the end. Okay, so I've leveraged here your very nice AiQyaM logo, which is really kind of at the heart of everything I'm going to talk about. So I really appreciated also the waves on the right-hand side here that you used, because at the end of the day, quantum has to do with waves at the one level, also discrete levels. But on the other hand, the hardware part of it looks more like these somewhat classical looking structures, chips, and we'll want to connect the two. So let's dig into that. And maybe people can post questions in the chat if they have them, and maybe Nilay or someone else from the leadership team can bring those up to me.
Yeah, definitely.
Awesome. Let me back out for just a second onto the very big picture. I mean, today, as you know, there's such a thing as the quantum cloud, and you can log into it from your laptop, and you can begin to execute, you mentioned cryptography earlier, you can begin to execute logical gates, Hadamard, S-gate, T-gate. You can do these things that until 10, 20 years ago were mostly just in the cloud space of dreams. But now they're in the cloud space of services that begin to look like this. This is one of these pictures of a superconducting quantum computer inside of here. There's also ions and photonics and other platforms, which is covered under your discussion. I'll focus mostly on superconducting qubits today. And inside of these machines, you can now begin to, from the cloud, execute programs in a familiar language, a classical language like Python. We can begin to also run, chemistry or cryptography programs or things like that, and you can get results. right? And you can begin to even simulate some of these very nice basic research questions about chemistry, molecules, and so forth. And a lot of the development, it actually is based also on classical ideas and tools, though it also departs into the level of quantum. So we can begin with some of our classical knowledge about electrical engineering, computer science, programming, coding, Python, and so forth. We can leverage a lot of that and begin to use it to now dive into a new realm, the realm where we begin to use quantum. And so a lot of what my work and the work at AiQyaM has been about is also been to enable that. And I think that's a statement throughout the broader community, because quantum is growing very quickly, and we're all trying to pick up these skills as we go along. Now, in particular, the entire quantum ecosystem, everything I've shown you so far, can only move, can only advance, can only progress as fast and as far as the hardware that underpins it. So it doesn't matter how good your quantum software is, if your quantum hardware can support it. And the pace of course, the expectations for quantum are proceeding, the pace of what we want to achieve and do and can do is moving faster and faster. Well, therefore, the innovation, the development, the design, the analysis of quantum hardware has to keep pace and accelerate as well. And so that's why I'm so excited about this community. I think it's the first community that's purely dedicated to well, if that is at all a quantum hardware focused community that I know of, other than maybe the Qiskit Metal software community, but that's more aimed around Qiskit Metal. So big kudos to you guys. You might be a world's first. I think that's something to be proud of. And it's key because everything, as I mentioned, rests from the quantum level, rests on the engineering as well as the software that goes around that, on that lower level of the actual understanding, designing of the quantum hardware and devices. And there's a huge gap in both the software that's needed, in the education that's around it, in the content, in the onboarding material. As we talked earlier today, a lot of this is still very scattered or missing. And so that's a great place for a community like this to come in and begin to tackle some of these problems, and to also take its members and lead them onto a more clear and definite path. In any case, the aim, I think, of a lot of what I've been thinking about, and my team here has been thinking about, is how do we make this easier? How do we make this easier so that we can focus on innovating, on being creative, on learning and the fun stuff of designing quantum devices? And so I'll mention a little more about Qiskit Metal, but I won't get into any of the details. There are lots of now tutorials online, and you guys are some of the great experts and users these days. So let me zoom out and give you more of the broader picture overview. Some of you might have seen this slide before, but the big picture of how quantum in the lab works to connect the pictures is that you start with your laptop. You can log into a cloud facility, such as this particular one here, that can itself house some environment for superconducting circuits. That's a cryogenic environment at negative 273 degrees Celsius. And at the very, very bottom of this fridge, of course, is contained a shield that itself houses the quantum processor, which is shown here in a picture from a few years ago. And as you can tell, at the end of the day, everything you run and execute goes through this chain all the way down to the quantum processor. That's the only thing that's quantum in this entire chain. Everything else is not quantum. It's just, classical in and out electronics, control, software, etc. But the real quantum aspect of the whole thing, that's the quantum chip. Then the real question is, how do we design these quantum chips? And the answer is that it's not actually easy to find a text that explains this. There's no textbook yet. There's some dissertations, a few scattered tutorials, but for the most part, this is something that we're just now beginning to streamline and create and do. And part of what Qiskit Metal is trying to do is to make this easier, and I think part of your community is also trying to in some sense help tackle this as well. At a very coarse level, there's the physical layout, which you can see with your naked eye. You can see pieces of metal on a substrate such as silicon or sapphire, which then themselves can be to a first degree seen as electromagnetic structures, LC resonators that oscillate at microwave frequencies, very close to those of your microwave oven. But it's different. You know, if you come from an electrical engineering background, all of this may be very, very familiar to you. If you come from a physics background, what might be very familiar to you is, you know, wave functions and Hamiltonians and things like that, but maybe not this side of the spectrum. So these two fields now have to join much more tightly than ever before, because these circuits aren't just regular circuits. They're cooled to such low temperatures, they become superconducting, and they can exhibit and mimic the properties of individual atoms. And so they can begin to give rise to potentials that support wave functions like this. And the question is, how do you understand all of this? How do you bridge those gaps so that you can then link the qubit properties, the qubit and chip design at the layout level to the actual properties in Hamiltonian of the physical device? And in practice, what we have to do is to optimize this so that we make the best quantum processors, or we make the next generation of qubits. You know, we still don't quite know, I think, what the transistor of the future quantum computer is. There are a number of ideas, and I think we have to keep innovating on that as well. And so we have to go over and over again in this feedback loop here, keeping this tight interaction between the engineering, the hardware, and the Hamiltonian or the physics part of it. And maybe you don't need to be expert in both, as long as you have that link. Now, I think overall, this is a miracle. I mean, just the fact that we can even begin to tackle this question of, you know, creating these big macroscopic quantum objects and engineering their quantum properties with precisions at the level of part per million. Even, you know, 10, 20 years ago, even at the start of my career in physics, people were still saying that, well, you know, gravity will come in and it will decohere your 2 qubits, or, you know, the statements like this, or 10 qubits, or whatever the number is. So the fact that we've come to this level is unprecedented in human history, and has far exceeded the rate at which I thought it would even potentially happen. So I'm always very excited by this. Now, there are, if you want to be very careful, a lot of questions to consider in designing a quantum chip. You know, if you see this quantum chip here, there are metals, junctions, dielectrics, readout structures, qubits, geometry, topology. And if you want to be very careful, you know, there's a number of questions you could ask yourself about the chip, about couplings and non-local couplings, input-output couplings, loss budget, how much energy is lost to this structure, how much energy is lost there, etc. So how do you heed all these needs and questions in a more kind of systematic way, and you don't drive yourself crazy? What does the process look like overall? Well, in a very coarse way, if we had to somehow summarize some of this, the way that you would think about designing quantum hardware might start with a concept where you roughly know that you want, say, 2 qubits or 4 qubits, and you want them of this type and that type, and they should have this interaction. Then the way you define that a little more explicitly is to say, what's their Hamiltonian, essentially, you know, what are the frequencies of the qubits, how nonlinear are they, how strongly coupled are they? Somehow you need to take that and turn it into a physical layout. And that's not an obvious process. This is where a little ingenuity, creativity, and experience comes in. And you can also use some pre-built ideas, such as in blocks. Then you need to make sure that what you have laid down or put down on your chip is actually doing what you want. And the way to do that is to first do some form of an electromagnetic analysis. Typically, this is actually quite a slow process because you have to wait for the simulation to finish, or run it, or set it up, and so forth. Then from that classical simulation, you need to do some quantum analysis that can now tell you what that classical structure corresponds to in a quantum world. And from there, you can then connect back to see how close to the ideal thing you wanted you are. And then you go back and forth in this loop until you've converged close enough to send your device over to fabrication. And part of what the project that Nilay mentioned, Qiskit Metal, aims to do is to simplify this as much as possible and to allow you guys, for instance, to just leverage the software to make this your life easier, so you don't have to implement all those steps manually. And you can use proven and tested methods as much as possible so that you can free yourself up for both the learning part of it as well as the part where you can design your device and or innovate and create new ones. And so Project Qiskit Metal tries to seamlessly interconnect these 4 key components. I guess we have the slide here where it was very nicely summarized by Forbes that the aim of Qiskit Metal is to make it so you don't have to be a rocket or a quantum scientist to design a quantum chip. You can begin to do this and leverage this even without having to have taken 20 years of courses on this stuff. And that's in the direction to fuel that fire in the furnace of innovation so that we can bring in our knowledge and our skills and our ideas from the different fields and tie this all under one umbrella. Now, in the study of quantum devices, there isn't always one description for every job. There isn't yet a strictly defined, well laid out path to how to design these quantum devices. There's rather a suite of techniques. It's not like CMOS, which has existed for decades. Quantum is very new. It's very dynamic. It's leaping from research to industry, from academia to industry. So there's still a lot of room for making your mark as well. And so a few of the ways we can think about these kind of structures is in kind of partitioning the Hamiltonian as systems plus interaction, or linear plus nonlinear parts. We won't get into that here, but rather I'll jump into the left side of this picture to show you now what, say, a 3-qubit device might look like, here depicted in the Qiskit Metal GUI. And in this particular picture, you have a couple of structures you might recognize that you can also draw pretty quickly. There's 2 qubits that are coupled by direct coplanar waveguide coupler. There's some resonators, which are these squiggly bus lines that couple to some different type of qubit, and so forth. And the idea is that you can start to take some of these building blocks, put them together pretty quickly. If you know what you're doing, you can make this design in less than an hour and begin to simulate it so you can understand what it does and how it interacts. If we get a bit more deep and a bit more technical to explain one particular flow of analysis that's also being merged into the metal workflow quite recently now, that I think is also closer to some of the traditional electromagnetic thinking of things, is to say that one thing you can do is to start with a guess layout. Let's say you want to implement a 2-qubit chip. You might say, okay, well, let me place down these particular 2 types of qubits here, which look like this, connect them by a little wire. I'll add some structure that allows me to read out what those qubits are. Now we can simulate each of the different blocks independently. So I'll take this particular little qubit, extract it into an external electromagnetic simulation, such as ANSYS, Q3D, or maybe HFSS. That simulation can then tell me exactly what the electromagnetic properties of the structure are. In this case, I'll look at a capacitance matrix. I can take that capacitance matrix and feed it into this lumped oscillator analysis. This is a particular paper we recently put out, which you can find now as a tool to use in Qiskit Metal. That will then give you will save you a lot of time to implement it yourself, and it will give you a final Hamiltonian of this structure by taking all the different pieces of the resonator, the one qubit, the other qubit, the second resonator, feeding them all together into this procedure described in this paper, and it will then tell you what the composite system of all the different pieces does together with all its interactions, without any approximations. You can then use that to not just understand the Hamiltonian, but as a next step, you can then use that to connect it to something like Qiskit Pulse, to look at gates on that system, to try to optimize particular two-qubit interactions or time evolutions, to understand also what the dissipation and noise will do to your system, and to really begin to optimize it. So this is one particular flow that you can begin to use and play with or understand. And in part, the way that works, for instance, is to say that I select a part of my layout, I export it into some electromagnetic simulator. There, I need to add all this extra information, such as is it a silicon, is the substrate a silicon, a sapphire, etc. Which pieces are metallic, which ones are some dielectric, and so on. And you can come up with various designs and then begin to analyze them or look at previous examples. Now, one question you might ask is, how do I know what to do? How do I know, in a sense, what analysis I have available to me or we can use? So I'll just point out that there are some tutorials, and by no means are these all exhaustive. And I think there's lots of gaps to fill here, lots of things to still add, lots of things to understand. But these can give a little bit of a beginning and a guide to some of the analysis that we use. And generally there's three types. So I just want to illustrate the three types to say that the first type that you might see is the one that uses impedance analysis. So these are scattering matrix curves, impedance curves, admittance curves. And this is something you can do, you can run also in the Qiskit Metal software. These are very familiar sort of basic tools to, or familiar tools to electrical engineers, when you use impedance-based analysis. And you can use some of that to then link to the quantum part. Now, that's not the only way to do these things. You can also look at capacitive analysis. You can extract capacitance matrices and create a larger effective code and go from there. So this is more the flow that I illustrated on the previous two slides. And then the final third category of analysis that you will see are based on simulating the full glory, power, and beauty of Maxwell's equations. For instance, if you do a capacitive simulation, you won't capture all of the strain inductances and microwave effects. But if you do a normal mode, eigenmode analysis, you capture all of that. But then there's certain trade-offs. Some analyses are faster, some capture some effects, some don't capture others. So this is some of the things you can learn and sort of alternate and understand as you dive deeper into this. And another key thing you do with any of these analyses is to sweep parameters. You can say, well, how close can my two qubits be? How far can they be? How strongly can I couple them by changing this dimension? Or how is the frequency of my qubit affected if I change the pads and make them circular, rectangular, or hexagonal? You can let your mind run wild here. And these are a key tool to that is to be able to sweep parameters. At the end of the day, you'll connect that schematic or that physical circuit to the Hamiltonian, the wave functions of your device. And I probably don't need to get too much into explaining what this picture means, since it is the logo of AiQyaM, of this group. So I'll let the founders of the group maybe explain that another time in more depth and detail, but you can essentially take your quantum structure and begin to plot these functions for your particular structure. Now you might ask, well, this is all very, very nice, but how well does it work? How well do real devices in experiment match up to the theory and predictions that these methods give? So here's a summary plot of 9 different qubit chips that were all in different architectures and so forth. And what you can summarize from this or learn from this is that over 5 orders of magnitude in energy of the predicted on the bottom, sorry, the predicted on the y-axis and the measured on the x-axis energies of the devices, we saw really very close agreement between predictions and measurements of these devices. For the frequencies of the qubits, we had something at like 1% agreement, and for different nonlinear parameters such as the antiharmonicities or qubit couplings, we had agreement at the 5 to 10% level as well. So overall, these methods, when implemented correctly, can be very precise, and they can give you this a lot of predictive power to design new devices. You can also look at methods at very small, fine couplings, and newer methods such as this lumped method or eigenmode method. And again, you can find agreement at the level of just a few percent. We don't need to look at the details of these curves. This is just to tell you that all the methods, when applied right, can be quite good. And some methods, like the energy participation method or this impedance method, will fundamentally always perform a bit better in the long term than, say, a method that is fundamentally based on approximations, such as capacitive, depending on your structure. So the statement here of this last few slides is to say that there isn't one tool for every job. That's why it helps to have a bit of understanding of the few different ways you can tackle the structure. There's sort of 3 classes of analysis techniques in superconducting circuits. You can use the lumped oscillator methods, which can be quite precise. They're very fast, but not as general. Or you can use full wave methods such as the eigenmode or impedance methods, which can also be very precise, but may need a bit more computational time and RAM. So to kind of zoom out and say a bit more about the vision of open source quantum development with Qiskit Metal, the idea is that we have experimentally tested methods and a library of components that the community can also help build out. We're trying to put in really cutting edge resources and papers that we're just publishing as we go and adding to the framework, while making things lightweight and extensible and flexible so that we can support the future designs that we haven't even thought of yet, and in the end to provide end-to-end automation. And the idea here is really that we're doing this together. I mean, Qiskit Metal and I think many other projects here very much are driven as a community thing. That's why AiQyaM is such a great thing, I think, is because it is forming exactly this community. So from the Qiskit Metal side, this call for community participation is very much in wonderful alignment here. And big part of that, I think, of AiQyaM's mission, as far as I can tell, and I'm excited for, is education as well, because these have to go hand in hand. As we're developing the tools, designing and innovating the hardware, we also have to understand and develop our understanding, train the next generation of folks, and go from there. You might ask, what are some of the devices that have already been made with Qiskit Metal or are being currently developed with Qiskit Metal? So I thought I would give you a quick showcase of a few studies. Here's a 5-qubit device that we made for the University of Tokyo internally at IBM. This is the actual device that was made. You can see it here. Chalmers made an 8-qubit device that was fabbed and measured, and these are some measured results and simulated results from them. TU Delft is in Europe, is building out this fluxonium device that they simulated in Qiskit Metal and found some really wonderful results. And there's a few others. One thing that in the last few minutes I'll just add and I thought was interesting is, and perhaps something of interest to the group, is that we had the chance to host a Qiskit metal hardware hackathon. And there was a challenge to design a 2-qubit quantum processor to spec. And there was 48 hours for the 3 or 4 teams who were doing this to do. And these are some screenshots from that particular hackathon. So perhaps an idea for the community here as well. I think with the community you're building, it's really wonderful to keep that tightly linked and meshed with the Qiskit metal community and beyond, of course. But I'll just point out that there are a number of tutorials that are quite helpful, by no means complete or extensive. And I think there's a lot of work to be done here also in live sessions. I know many of you are very active in the questions and answers on Slack. So maybe, I don't know what fraction, but a large fraction of these 1,800 Q&A questions are definitely from members of this group. So very thrilled for that. Big kudos to you guys. I know you have also very attentively watched the Global Summer School lectures. I think these are a good way to learn more. And we had some discussions of maybe doing a more in-depth collaborative project with you potentially on that. I'll mention there is, of course, the Qiskit textbook, which you've mentioned as well. The Friday seminars, these are more advanced seminars that I host every Friday at noon Eastern time with some of the leading authorities on upcoming scientists on quantum hardware and software and design. And of course, you have full access to all the open source software development kit for Qiskit Metal. And a great way to get help and get in touch with us is to contribute to that open source, to make a pull request, because then you'll get feedback from us directly on it, line by line comments, and staying in touch on the Slack is always a great way to learn and build. So I think with that, it's been my absolute pleasure to share these few thoughts. And I'll leave you with this thought, which has quite often kept me going, since this is a lot to jump into, a lot to learn. And I think the main thing that has worked for me is to think of this quote, which is that it's enough if one merely tries to understand or comprehend a little of the mystery of quantum hardware each day. And if you got just a little tiny bit out of today, I think that's a big success. So with that, thank you very much, and I'll take any questions you may have.
Thanks a lot. That's actually a very good, like with drop by drop, you can build up an ocean. So we have a couple of questions down there. The first question is like a 2-part question. The first part being why we have different qubit layouts / maps in IBM-Q systems, and not every system follows a fully connected qubit layout like a grid. And the second part is like, what is the importance of topology of qubit maps?
Great question. Yeah, so let me go back to even this slide here. You can see that there's so much variety between the design on the left, this design here from Chalmers, this one, obviously the IBM quantum maps. And I think as some of the IBM research blogs have written, and some of the papers we've done have written, there are trade-offs, right? What you notice when you do these simulations is that if you put a qubit and you try to couple it to every other qubit, there are just too many spurious interactions. Part of that is that you want your qubits to be individual building blocks, and you want them to interact in a very deliberate and isolated way to only one other qubit or 2 other qubits, depending on your structure. So if you have an algorithm that requires all-to-all connectivity, that's at odds with the way the hardware usually operates, because for a graph that requires all-to-all connectivity, you'd like every qubit to be connected to every other one. But from the point of view of the quantum hardware, if every qubit is connected to every other qubit, then that tends to just cause, the problem becomes just very messy, because there are too many spurious interactions that are uncontrolled when you have so many things coupled to each other that you need to simultaneously try to optimize over, and it becomes a nightmare very quickly. So part of the designs and the way you see them laid out is a compromise between connectivity and isolation and purity, if you want. That's sort of a high-level answer. And part of, and a lot of them are motivated by particular algorithms, whether it's, surface codes or other types of, embeddings that can fit onto a graph. So hopefully that gives you a bit of a general flavor.
Yeah, and I guess about the third question about how to join AiQyaM, I guess you can get in touch with any of us. We'll help you with that. Not further questions in the chat. I guess anyone who wants to ask a question, they can unmute and yeah.
Yeah, there were a few questions. So we released out a form before the event, and there were a few questions in that. So I'll just go ahead and ask them. So so we have a diverse group of people in our community here. So there are a few people from mechanical engineering background. So what are some areas of innovation or scope of research that like a mechanical engineer can pursue for quantum hardware?
Yeah, great question. So there's obviously the directions I've talked about already, which are more focused on the quantum processor and the design of the quantum processor, and which don't involve too much of the mechanics directly. Apart from the fact that the way to understand actually a lot of this theory is through sort of mechanical equations, Lagrange's, Hamiltonians, if you want to get into it. So actually that if you have that knowledge from mechanics, it's almost the same with electrical circuits. The math is almost one-to-one. In fact, I read a lot of classical mechanics books to understand what happens here usually, because the mapping is essentially one-to-one. So that aside, there are many questions that do involve a little more of the mechanics. Mechanics is a super broad field. I mean, it involves, thermal analysis, strain analysis, there's so many fields, but there are a few questions that pertain to the chip and what's outside the chip that more directly involve the mechanics. So this chip has to fit inside a sample holder, right? How is that sample holder designed? How does it fit with the chip? How do the input-output cables and routing work, especially when you take into account all the thermal shrinking and contraction that happens between room temperature and absolute zero of all the different materials. So you certainly have all of that to also take into account. Then on the infrastructure of the rest of the quantum computer, there are many questions related to the thermalization and the actual, I didn't show a picture here of the input output cabling, but it's sort of few diameter, it's a meter wide construction. So there are quite a few questions on that side of the front as well. So hopefully that gives a flavor, and feel free to elaborate more.
Yeah, thanks a lot. And I can see another question here. So it's a bit controversial question, but
okay, I give up.
By what? So what is the approximate time frame for seeing like a maturity in quantum hardware, and like it can be with respect to superconducting or any other types of quantum hardware architectures? So
yeah, that's a great question. I mean, maturity is such a, when we say classical hardware matured, it's a little hard to say. In 1946 or 7, when the transistor was invented and began, nobody imagined the iPhone yet. So from our modern eyes, that hardware back then was very, very immature. From my eyes, from just a few years ago, even this like 5-qubit chip here is, it's kind of like, it's getting more mature. So that's very subjective. I think we're almost at the level of 100 qubits in superconducting circuits, and in the other platforms at the level of control and coherence. Anyone can build 1,000 qubits, tonight, but almost no one can build 100 qubits that are really well controlled and isolated and high coherence and so forth. You can make many qubits very bad very quickly. That's easy. Making a few qubits really good repeatedly, that's very hard. So we're just, I think, starting to get to the level of sort of 100, which is a big level, and then 1,000. I think that's sort of maybe the turning point. And I think it's the IBM roadmap. On the IBM roadmap, we've committed to 1,000 qubits in 3 years or so. I forget the exact number. It's about 2 or 3 years. It's very, very soon actually. So I think at that point I would consider the hardware to be becoming a lot more mature. Now I don't want to say mature, because I still think we have a very, very long way to go to full-fledged quantum computers. But 1,000 to me sounds like a whole lot.
Yeah, that's definitely true. Yeah. So,
Sir,
I think someone has a question. Yeah, please go ahead.
yeah, may I pose a question?
Yeah,
Yes,
sure.
Akhil.
Sir, so what is this kind of quantum mechanic? I'm sorry, what is this kind of quantum computer science different from the original we have right now, sir? So how would this change our lives? Maybe.
How is it different from what? Sorry.
So how is this quantum engineering in computer science different from the normal hardware and software technology we have right now, sir? So how this would change our technology?
Yes, well, it's a whole different technology stack altogether, right? So if I go back all the way to my beginning, the current quantum computer looks like this. It looks nothing at all like any of the classical computers. So just to set the context straight, right? This is not making anything different better for classical computers. This is a whole different technological tree. There's a reason for why we want to pursue that, and some of the things that it provides that no classical computers could potentially ever provide, that have to do with potential exponential speed up on a number of interesting problems. But from the point of view of the technology, it's a different technological tree altogether. So hopefully I managed to address your question.
So now we are using capacitors to store temporary memory, sir. That is the zeros and ones we are storing using capacitors, sir. That is random access memory. So in quantum computer, are we going to use capacitors or will it change?
It's a good question, but that those capacitors, what's different about quantum is that if you can't even afford to lose one photon of energy, right? Because that's your entire bit in this case, and your capacitor is very huge, right? You can't afford a single photon of noise to enter. I mean, a single photon of noise, that just think of how small of noise that is. So any of those capacitors we use for classical circuits, they're way too noisy. They can't store and control the quantum information. The quantum information there gets totally obliterated and destroyed, basically instantaneously. So that's why we have to reach to new technologies like superconducting quantum mesoscopic circuits, or ions, or photonics, to look at controlling nature at this very different fundamental level. So we can leverage some of the knowledge we have about classical capacitors and what structures are good or not. But the constraints under which we do this for quantum computing is quite different. You notice a lot of the structures showed are very large. Maybe I didn't have too many scale bars, but you can see them with your eyes. They're sort of 50, 100 micron pitch size things for the pads of the qubits. That's because you want to also minimize material losses. So the larger you make the structures there, the less susceptible you are to these minute atomic size imperfections. And so it's quite a different technology in that sense. But it can leverage a lot of what we know. I mean, coplanar waveguides, that's been invented, decades ago, right? And we can leverage and use that into the quantum, but we need to tailor it and reshape it for these new conditions.
So if we're gonna switch to artificial intelligence technology in the future, will this quantum computer be useful in that technology, sir?
Maybe
yeah, go ahead.
I can just interrupt here. Sorry for that.
Oh yeah, maybe we have to
So
let you
yeah,
proceed with the meeting. Of
I
course.
see a really interesting discussion going on here. But I think we can take up some questions, some of these questions online, offline as well. And due to the restrictions of the time, I would have to cut you off, Akhil. Sorry for that. But yeah, these are definitely interesting questions, and maybe you can email it to us, and we can forward it to Zlatko, and uh, yeah. So yeah. So maybe one last question that I had in the forum was regarding. Are there any improvements that we should look forward for the Qiskit Metal project? Like, would you like to give a teaser for something?
Oh, do you mean improvements that are already coming or improvements that we would like to see?
Okay, that are already coming, maybe.
Ah,
So
yes.
yeah, the person didn't specify what they were asking. So yeah.
I see. Great. So, I mean, one thing I'm really, really looking forward to is actually to this process. I think we're just about to launch this in a couple of weeks. And now it's fully. There was an earlier version of this that kind of worked, but now I think we've got a much more general framework, and I think I'm also excited to begin at the level of like schematics as well and connect. So you can draw capacitors and inductors and work with the Hamiltonians and to make this very friendly and useful, so that you can sort of tailor and optimize things at the level of a schematic, L's and C's, get a Hamiltonian, and then later go back and connect the layout to that schematic. But I think this new workflow here is something I think is very powerful, and I'm really excited about.
Yeah, that's great.
Yeah, with that,
And probably one last question that came up in the chat just now. Is a background in quantum mechanics and quantum information sufficient to understand the underpinnings of quantum hardware, or do we need something else as well apart from that?
Good question. So you said quantum physics and quantum information?
Yeah,
Yeah, I
quantum
mean
mechanics. Yeah.
that's my background. My background is quantum physics, quantum mechanics. So I would hope so. Obviously, there's some extra things about layout and so forth, but this is stuff you can pick up really on the go, and a lot of vice versa. And even if you don't have too much of the quantum background, a lot of what's happening is to begin to abstract that a little bit into more models. I think maybe Beer in LA or someone earlier was talking about this as well. That increasingly maybe we'll move towards more models of so that you don't need to know 20 textbooks worth of knowledge to actually begin to do this as well. And I think we're trying to help make this a little simpler here as well, so you can leverage the tools without having to understand all the details under the hood.
Mm-hmm. Yeah, that's great. So yeah, I don't see any more questions as of now. So thanks a lot, Zlatko. And yeah, we hope to stay in touch with you even like for a much longer time in the future.
like the coherence time between us getting tuned should be like infinite.
Yes, that wonderful conference time. Yeah, thank you very much again. Yes, I'll stop sharing and I'll let you. I think you had more slides to show, but it's been really wonderful.
Yeah, so we'll just finish off regarding AiQyaM and just a second. Yeah. So Nilay talked us about through the motivation of starting AiQyaM, and we had a really good presentation from Zlatko regarding the current progress in quantum hardware and like a lot of things, a lot of new things about Qiskit Metal and how to use it, how to learn new things. So as a community, we at AiQyaM are also planning to come up with something similar. And as Archit already mentioned, we are now a part of the IBM Quantum Educators program. So, talking about the vision and mission of our community, we first of all we like want to develop a strong network of various quantum hardware enthusiasts and researchers. And throughout this process, we have like three important missions. So the first one being to promote quantum hardware knowledge by conducting talks and webinars and uh, different informational sessions by distinguished researchers around the world, like Zlatko himself. And also to provide some more learning resources and create new course content as well as a part of the Quantum Educators program. The second one being to collaborate with some premier research institutes and industries to take this field and this uh, area of research forward. And not many people are working in quantum hardware, so we want to be the guiding force that maybe we can provide a platform for the people who are aiming to start with quantum hardware, or even who are working in quantum hardware and they want to collaborate with different researchers around the world. And the final and the most important mission is to provide a uniform platform so that people from different backgrounds, as I mentioned, there are a few people from mechanical engineering and electrical computer science, and even from physics and chemistry backgrounds, who are interested in this. So to provide all of these people a unified platform to like discuss and develop ideas about quantum hardware, and to maybe potentially make quantum hardware which is focused to some particular application, like for example an accelerator for Shor's algorithm. Something like that. So, yeah. And talking about the roadmap, it looks something like this. So we have the few main points that we want to develop a unified ecosystem in India, and then also gradually transition towards being a global community, and then provide a unique platform so that industry and academia can have good collaboration among themselves for quantum hardware research, and also conduct some research within the community for different quantum hardware architectures. So we just now heard from Zlatko about superconducting quantum hardware. There are quite a few different types of quantum hardware architectures, and as of now we will be starting with three of them. So superconducting, we have already started working on it a bit using the Qiskit Metal project, and we were working on it through the Quantum Hardware Learning Circle at QCI, Quantum Computing India, and we have started making some small 2 to 4 qubit chips. And now we plan to expand our horizon and also go into trapped ions and photonics. So we have started a little bit of research in that area, and we plan to go ahead and try to establish a pathway so that the people who are beginners, as well as right now researching in quantum hardware, they can get into collaboration with us as well as with each other. And this is what the tentative community structure looks like. So we'll have recruitments for apprentices, and then those apprentices can after a certain time they can get promoted to junior or senior research associates, and then out of those we will have vertical heads as well. And of course we also are aware of the fact that there might be people from different backgrounds and different skill levels. So if your skill level matches the skill level of required for a junior or a senior research associate or even a vertical lead, you can directly join at that position. And those details I won't cover in this particular presentation, but you can always reach out to us and contact us through our email or through LinkedIn, and we'll be in touch with you if you're interested to join AiQyaM. And yeah, so with that, thank you everyone for joining our launch event, and thanks a lot, Zlatko, for such an inspiring talk and such a good talk on quantum hardware.
Yeah, especially like will really appreciate, because it's like somewhere near, I would say 10:30 in the night over there. Yeah, thanks for staying up late for us.
Yeah. So I would also request a small word from Sam here. So he is the head of Quantum Computing India, our sort of parent community / organization. So Sam.
All right, thank you, Abir. All right, so most of you know about Quantum Computing India. So we started off almost 1.5 years ago with the vision of creating more quantum-related startups and community out of India. Then the way we define community also mattered a lot. So on one side, we are skilling people on through different means. So one of the ways, apprenticeship, learning circles, and learning circle in turn culminates in creation circles, where you're trying to come out with a use case out of that. And as Archit and Nila already pointed out, so they joined us as an apprentice, then Abir joined from quantum cryptography, hardware, then quantum hardware learning circle happened. And now it's so happy, and I'm elated to say that, to see this happening, like Abir was saying, like a parent company or like a parent community, however you want to look at it, right? So our vision is to have multiple such communities. So quantum hardware is great. So we have quantum machine learning circles. It hasn't become a community yet. So a community essentially is what you put in, you can take as much out of that, right? So I mean, most of you here are aware of that. We also have a structured learning path apart from learning circles, which really depends on the kind of people who join your learning circle. So one of the good things that we did in quantum hardware learning circle was we didn't invite everyone. We conducted an interview and we shortlisted few people who are serious about this, and like, those people came in. That's one of the main reasons why this has become a separate community of its own. So we are also learning in terms of community building, how to take it ahead into the future. So that's one side, right? So you're skilling, you're learning and whatnot. So the structured way of learning is through fellowships. And this, you're like upskilling yourself in different levels. So now you can think of these 4 levels. Some communities even have 10 levels of skilling, right? And what moves you from one skill to other, that also involves contribution or the capital side of things, which is the demand side. So the work that we are doing culminates into either a research paper or a POC, and that becomes a selling point for our growth team, essentially to go and create a market out of that, right? So that's our whole vision, which is to create startups and communities, not just within India, it has gone outside India as well. Now, AiQyaM will be a global community, of course. Yeah, so any other questions, you guys can always ask us. This is purely about quantum hardware, and I'm really proud to see where we have reached, and to see a lot of people who have joined us from the beginning as well to hear. All right. Thanks a lot, guys, for staying with us. Any final thoughts? I think Achit will put up the Discord link for AiQyaM. You guys can join that, and the actual community events will kickstart from Jan. But like in between, whatever we are doing with QCA fellowship and everything will be intimated to you guys over there. Yeah. All right. Thanks a lot. Over to you, Abir and Nilay. Yeah.
Thanks a lot, Sam. And so Archit will just be posting the Discord link, so you guys can join. And yeah, thank you, Zlatko. Thanks a lot for for your time, and we hope that we'll stay in touch for much longer.
Yeah. Thanks a lot, Zlatko.
Thank you, guys. It's really
Thank you,
appreciate.
Praveen. Yeah.
It was very nice. Yeah. Thank you, Zlatko, and you guys did an amazing job. And I was enjoyed as part of the QCA and also the hardware fellowship plus hardware circle too. So thank you very much, and I'll keep in touch. Yeah, for the learning. Yeah, thank you.
All right. Thanks a lot, Praveen. Yeah.
Yeah.
Thank you,
Guys.
everyone.
Good luck.
Bye-bye.
Yeah. I guess with any other questions, guys, you can get in touch with any one of us, email it, send it on any of our platform. We'll definitely get you back on.